Ever pondered about the origin of the universe? How did everything come into existence? These are questions that have stumped humanity for generations. The most popular explanation, as most of us know, is the Big Bang Theory. But what does this theory really entail? Well, it all begins with something known as a singularity. Imagine a single point so compact yet teeming with infinite heat and density, a point so small and intense it's almost impossible to comprehend. And this, my friends, is where our universe as we know it had its humble beginnings. About 13.7 billion years ago, this tiny singularity expanded and stretched, kick-starting the birth of the cosmos. From a point so minuscule it's practically non-existent to the vast, ever-expanding universe we find ourselves in today. Imagine, everything that exists was once compressed into a minute singularity. Fascinating, isn't it? Now, let's move forward from that singularity. What happened next? Well, as the universe expanded, it cooled. But then there came a point when this expansion mysteriously halted. This period is known as reheating. During this time, a flood of matter and radiation began to fill the universe, giving birth to the elements we know today. Atoms, particles, and the stuff that would eventually form stars and galaxies all started to take shape during this reheating phase. Imagine the scene. The universe at this point was a blistering cauldron with temperatures around 10 billion degrees Fahrenheit. That's hotter than the core of the most massive star. And amidst this unfathomable heat, a variety of fundamental particles, including protons, neutrons, and electrons, were born. These particles were like the first bricks in the construction of the universe as we know it. This early universe was a soup of particles so dense and hot that it was essentially invisible. Light, or photons, was scattered around just like sunlight scatters from the water droplets in clouds. But as the universe continued to expand and cool, these free electrons began to meet up with nuclei and formed neutral atoms. So the building blocks of everything we know today came into being in such extreme conditions. Isn't that just mind-blowing? Here's a thought. Was the early universe dark? Imagine the universe as a thick, opaque soup, simmering with energy, yet unable to hold visible light. Picture a world where free electrons scatter light like sunlight bouncing off water droplets in a cloud. It's a world invisible to the naked eye, a universe in darkness. But hold on, the universe wasn't destined to remain in the shadows. Over time, these free electrons began to join forces with nuclei, forming atoms. These weren't just any atoms, but atoms with a balance of positive and negative electric charges. Atoms that could finally hold light. This monumental shift happened around 380,000 years after the Big Bang. And just like the flick of a switch, light was finally visible. The universe, once shrouded in darkness, was now bathed in light. And that's how light entered the universe, brightening the cosmos. Ever heard of the afterglow of the Big Bang? It's actually known as the cosmic microwave background, or CMB for short. This is the light that was made visible around 380,000 years after the Big Bang. Now, this wasn't discovered right away. Oh no, it took us until 1965 to stumble upon it. The credit for this accidental discovery goes to Arno Penzias and Robert Wilson. They were just trying to construct a radio receiver when they noted temperatures that were higher than expected. At first, they blamed it on some pigeons and their mess. But even after a good cleanup, the anomaly persisted. Meanwhile, a group at Princeton University was actively seeking evidence of the CMB. When they heard about Penzias and Wilson's peculiar observations, they realized that the duo had inadvertently discovered the CMB. So, an accidental discovery gave us evidence of the universe's fiery birth. So, how far can we see into the universe today? Well, it's quite amazing, really. Even though we estimate the universe to be roughly 13.7 billion years old, our telescopes allow us to peer an astonishing 46 billion light years into space. Isn't it mind-boggling how we can gaze billions of years into the past? What are your thoughts on the Big Bang Theory? Drop a comment below. Well, the most popular theory, the Big Bang Theory, suggests it all started around 13.8 billion years ago. Picture this. A point in time where the universe was a blank canvas, filled with matter, radiation, and the essential building blocks that would eventually churn out stars, galaxies, planets, and even us, humans. Now this is where it gets a bit tricky. In a universe where light travels at a constant speed, one might think we could see as far back as the universe's age, multiplied by the speed of light. roughly 13.8 billion light-years. However, that's far from accurate. In reality, the actual diameter of the universe is a staggering 92 billion light-years, with a visibility range of 46 billion light-years in all directions. So how far can we see into this vast universe? It may seem like we can see 13.8 billion light-years into the universe, but that's not entirely accurate. Let's clear up a common misconception about the size of the universe. You might think that our universe, being 13.8 billion years old, would have a diameter of 13.8 billion light-years. That's a sensible assumption, considering that light travels at a constant speed. However, the universe has been pulling a fast one on us. The actual diameter of the universe is a whopping 92 billion light-years. Yes, you heard it right, 92 billion light-years. And if you're wondering how far we can see into this vast expanse, it's about 46 billion light-years in all directions. It's like standing in the center of a giant cosmic bubble. But why is this so? Let's explore 3 intuitive ways to understand this. Firstly, consider a universe where light travels at the speed of light and matter is present everywhere. This is how most of us intuitively view the cosmos. Picture a universe teeming with galaxies and stars, all formed not too long after the dawn of time. Since light travels in a straight line at a constant speed, the longer we wait, the farther we can see. So, after approximately 13.8 billion years, it might seem reasonable to think we can see nearly as far back, subtracting only the time it took for the Big Bang to kickstart the formation of stars and galaxies. Now let's add another layer of complexity to this. Imagine a universe where not only is light traveling at a constant speed and matter is everywhere, but all matter can also move through space. This means that there are countless light-emitting objects moving in relation to each other. According to the laws of special relativity, they can travel up to, but not quite at, the speed of light. So it's conceivable that you could see twice as far as in the first scenario. If the object's light is only just reaching us now and they're moving away from us at nearly the speed of light, then they could be as far away as 27.6 billion light-years. But these views are not entirely accurate. There's a third way to view the universe. In this perspective, the universe is not only filled with matter and light traveling at a constant speed and matter that can move through space, but the universe is also expanding. Galaxies and stars are not just moving, they're moving apart from each other. This is the most counterintuitive layer of all, but it's the one that aligns with our current understanding of the cosmos. In this view, even though light travels at the speed of light, the universe's expansion means we can see even further than we might initially think, but we'll delve deeper into this fascinating concept in the next scene. The third and most accurate view considers the universe as expanding, with matter present everywhere and light traveling at a constant speed. It's a little brain-bending, but stay with me. Yes, matter is plentiful and rapidly forms stars, galaxies, and even larger structures. And yes, the light this matter emits travels at a constant speed known as CE. But here's the twist. This matter is also moving through space, primarily due to gravitational attraction between various regions. The universe isn't static, it's expanding. As it expands, the galaxies and stars move away from each other. This movement, in combination with the constant speed of light, means we can see much farther into the universe than just 13.8 billion light-years. In fact, we can see as far as 46 billion light-years in all directions. Now here's a thought. How useful is it to view events from billions of years ago, or do you think that engineers and scientists should be spending their time on better projects? Let us know in the comments below. Ever wondered why a far-off galaxy appears redder than it should be? No, it's not blushing. It's a phenomenon called redshift. Now, let's break this down. Imagine a loud siren blaring on a speeding fire truck. As the truck races past you, the siren's pitch seems to drop. This is due to a change in the frequency of the sound waves, a phenomenon known as the Doppler effect. The universe works in a similar, albeit more complex manner. When a galaxy is moving away from us, its light appears to stretch out, shifting towards the red end of the spectrum. This shift towards longer, redder wavelengths is what we call redshift. It's like the universe is a grand cosmic orchestra with each galaxy playing its own unique tune. The further away the galaxy, the deeper and more red its tune becomes. So the redness you see isn't a celestial makeup, but a cosmic dance of light and speed. Now, if you think the universe is a static canvas, you're in for a surprise. It's expanding, constantly. You see, the universe isn't just a grand cosmic stage where galaxies and stars perform their celestial ballet. It's more like an ever-growing dance floor. As space expands, the distance between galaxies increases, and it's this growth that adds an interesting twist to our redshift story. Imagine you're throwing a ball, but as it travels, the field you're playing on stretches out. The ball would take longer to reach its destination, right? Now replace that ball with light from distant galaxies. As space expands, the journey these light particles undertake becomes longer, causing them to stretch and shift towards the red end of the spectrum. So next time you gaze at the night sky, remember you're witnessing a grand spectacle. The universe stretching itself in a never-ending cosmic yoga.
The world is said to be a big place, but the universe is much bigger. And what's more is it's expanding all the time. How do we know this? Because of the evidence provided by redshift. In this video, we're going to learn about Edwin Hubble and his use of the Doppler effect as evidence of an expanding universe. Before the work of Edwin Hubble, scientists believe the universe was a lot smaller and static. Edwin Hubble became a famous American astronomer after he examined the light from nearby galaxies. The atoms of elements that are in the atmosphere of a star absorb specific wavelengths of light. This can tell us the chemical makeup of the star, as well as its relative distance from the Earth. We can see the absorption of these different wavelengths when looking at the light spectrum of a star, also known as Fraunhofer lines. The black lines show us where light is being absorbed. We can tell the exact wavelength of light being absorbed. The Doppler effect is the observed change in wavelength and pitch of sound, or change in wavelength and color in light if the source is moving relative to the observer. Have you ever heard a police car pass and noticed the sound of the siren change suddenly? Then you have experienced the Doppler effect. The same thing happens to the light of the stars traveling to us from distant galaxies. When a star is moving away, the light from the star, because of the Doppler effect, is of a lower frequency than expected. It moves towards the red frequencies, redshift. Hubble noticed that most of the galaxy's light was shifted towards the red end of the spectrum, and also the further away a galaxy was, the more its light was redshifted. Look at these two atomic spectra, one from our Sun and the other from a distant star. Remember, low-frequency visible light is red and high-frequency visible light is blue. The lines in the spectra are the same pattern, but they have been shifted to the red end of the spectrum of the distant star. Hubble concluded that most galaxies were moving away from our own. The further away a galaxy was, the faster it was moving away from us, and the universe is expanding. Look at these three spectra. Which of these stars is closest to us? Which of these stars is furthest away from us? Redshift also provides evidence for the Big Bang Theory. You can find out more about the Big Bang Theory in this video. So that's how we know the universe is a big place and expanding all the time.
Amazing how the universe continues to expand every second of every day. This question, my friends, is not just a philosophical one, but deeply scientific. So let's dive into the intriguing enigma of our ever-expanding universe. Consider this: as the universe grows, space itself expands, and as space expands, so do the wavelengths of individual light waves. Now, this might sound like a mouthful, but bear with me. Imagine you're trying to observe a light from a distant galaxy. The light reaches your eye, but you encounter a conundrum. How, pray tell, do you determine whether this light is a result of the galaxy's motion or the fabric of space itself, stretching like a cosmic rubber band? Well, here's the kicker. There's a relationship between the observed brightness of a galaxy, which is a function of distance, and the redshift. Redshift, for those who might not be familiar, is a change in the wavelength of light that happens when an object is moving away from the observer. So the farther away a galaxy is, the more its light is redshifted. Now let's throw a little more light on this relationship. In a universe that isn't expanding, the maximum distance we can observe is equal to twice the universe's age. That's a whopping 27.6 billion light years, give or take. But here's where it gets really interesting. We've already observed galaxies that are even farther away. Yes, you heard that right. In our universe, which is very much expanding, we've spotted galaxies that are at an even greater distance than 27.6 billion light years. So what's the secret? How is this possible? Well, my friends, that's a mystery we're still unraveling. In a non-expanding universe, the maximum distance we can observe is equal to twice the universe's age, or 27.6 billion light years. But we've already observed galaxies farther away in our expanding universe. Ever wondered how far we could see in any direction in the universe? Let's dive into this intriguing cosmic conundrum. You see, the farthest objects in the universe, the distant stars, galaxies, and even the faint echo of the Big Bang would only be about 41.4 billion light years away if there was no such thing as dark energy. But hold on to your hats, because in a universe where dark energy exists, this cosmic yardstick stretches even further to 46 billion light years. That's right, dark energy not only sounds cool, it also gives the universe a bit of an extra stretch. Now, if we add everything up, we find that the universe is a whopping 92 billion light years across at the farthest point that we can see. That's a road trip you wouldn't want to take without a good playlist. Now, let's say we were to pack our bags and leave today at the speed of light, a leisurely 300,000 kilometers per second. Even then, we could only travel about 1/3 of this incredible length or cover just 3% of its volume. The universe's expansion and the existence of dark energy would keep 97% of the observable universe tantalizingly out of reach. Talk about a long-distance relationship. So while 92 billion light years might seem like a lot for a universe that's only 13.8 billion years old, it's the perfect size for the universe we have today, filled with matter, radiation, and dark energy, and governed by the laws of general relativity. The universe has become as large as it appears to us because space itself is expanding, and new space is continuously being created between the galaxies, groups, and clusters of the cosmos. It couldn't have turned out any other way given what's in it, what governs it, and how it came to be. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content.